In this video, we'll start looking at a new genre of methods called nonparametric methods by looking at a regression method called K-nearest neighbors regression. Let's remind ourselves of the regression framework. In the regression framework, we assume that the quantitative response variable y is some function f of the predictors x plus an error term. Our goal in supervised machine learning is to estimate the function f from training data. At its base, this is a hard problem. This function f could be anything. How can we tackle this difficult problem of learning f? In what are called parametric approaches, we make simplifying assumptions about f by assuming that this function takes a particular form. The tool of linear regression, which is what we've been concerned with so far, is an example of a parametric approach. We assume that the function f is this linear combination of the predictors. The term parametric approach gets its name from the fact that the exact form of a parametric model is determined by the values of the model's parameters. In the linear regression model shown here, the parameters are the beta coefficients. Parametric approaches are useful if we don't have a ton of data because we've simplified the problem. We've reduced the problem of learning a completely arbitrary function to learning the values of a handful of parameters. In the linear regression model here, learning f amounts to learning the values of the p+1 beta coefficients. This is easier than trying to sort through the infinitely many possible functions that are not linear combinations of the predictors. But at the same time, the parametric linear model form we've assumed here can be viewed as rather restrictive. Why that particular function and not something else? So in a parametric approach, we simplify the problem by assuming that f takes a particular form governed by parameters. In a non-parametric approach, we try to make as few simplifying assumptions as possible. No method is free from assumptions, but in non-parametric approaches, we try to make much less restrictive assumptions about the form of f. Let's look at an example of a non-parametric approach for regression. Instead of assuming that f takes the linear regression model form, we assume that cases that have similar predictor values should have similar response values. This is a far less restrictive assumption about the form f could take. This assumption actually informs the idea for a method called the K-nearest neighbors algorithm. This approach is as follows. For a case I in the test set with predictor value xi, you find the k cases in the training set whose predictors are closest to xi. These cases form the neighborhood ni. This neighborhood is the term we give to the collection of cases that look similar to test case I. Note that to define how close two cases are, we need to have some sort of distance metric. Commonly, the Euclidean distance metric shown here is used. But there are many, many different types of distance metrics. Euclidean distance happens to just measure the diagonal distance between 2 points in space. Once we have the k cases that are closest, most similar to test case I, we predict the response value for case I as the average of the responses of the k cases in that neighborhood. Note that we can vary k to tweak or tune this method, and as such, k is a tuning parameter of the k-nearest neighbors regression method. For example, let's say that our training data consists of a predictor x and a response y, plotted here on the left. Let's say that we have a case in the test set whose predictor value x is 3.5. The k-nearest neighbors algorithm for k equals 3 would find the 3 cases in the training data with the closest predictor values. These points are highlighted in red, and they form the neighborhood for this test case. The x on the plot indicates the average of the y values for those 3 points in the neighborhood, which is the prediction we would make for this test case. We can repeat this process for all possible values of x. The curve shown in red shows the prediction we would make for any test set observation. We can also say that this is a visualization of the function f learned by a 3 nearest neighbors algorithm on this training data. We can do the same for k equals 1 and k equals 10. Note that as k increases, the function we learned gets smoother. Why is this? When k is small, a prediction for a given x is highly sensitive to who its neighbor happens to be. That is, a prediction at a particular x value is highly variable because it depends heavily on the very particular case that happens to be the one closest. This is similar to the idea that when we use high k and k-fold cross-validation, the error estimates in the iterations are highly variable. The high variability in the predictions for KNN regression decreases with higher k because we are now averaging responses from more neighbors, and an average over more observations is more stable. The difference between small and large k is a classic example of a phenomenon in machine learning called the Bias-Variance Tradeoff. The Bias-Variance Tradeoff is a hugely important theme in machine learning and provides a conceptual framework for thinking about tuning parameters in machine learning methods in general. Let's discuss this trade-off in more detail. The bias-variance trade-off represents a trade-off between two statistical properties of machine learning methods, bias and variance. Bias is the answer to the question, how far are model predictions from the true observed values on average? Bias ends up being a function of model complexity or flexibility. A highly complex model is one that has a lot of components to it. For example, a regression model that includes a lot of variables. A synonym for complexity is flexibility. A highly complex model can also be thought of as being a very flexible model, because its many different components can flexibly allow the model to look many different ways. For example, a regression model that includes a lot of variables has a lot more room for variety in its coefficient values because there are so many coefficient values. A model with high bias is an overly simple one. Overly simple models have high bias because their simplified depictions generally translate to a lot of error. Variance is the answer to the question, how much would the estimated model change if I had new training data? A highly variable method would result in us estimating a very different model with just slightly different training data. Bias and variance both contribute to test out of sample performance of learning methods. And generally, bias and variance are inversely related. When we vary tuning parameters of statistical learning methods, we're trying to adjust the flexibility or complexity of the resulting model to adjust bias and variance. But because of their inverse relationship, when we succeed in decreasing bias by making a model more complex, we end up increasing its variance. And when we change the tuning parameter to decrease variance, we end up increasing bias. Let's look at this concretely for the KNN regression example. When k equals 1, the method of one nearest neighbors regression, we are in a low bias setting because the function learned is very jumpy. It's very complex. At least it's definitely not smooth and simple. But it's this very complexity which makes it a highly variable method. The function we've learned from this method is not at all smooth. It jumps around a lot and would change drastically with even slightly different training data. When we move to k equals 3, bias increases because the function we learn is smoother and less complex. Our representation of the data is simpler. But the function looks smoother and seems to be doing a better job of capturing the general trend. This is even more pronounced for k equals 10. The themes we can notice here are actually quite general to machine learning algorithms. Overly flexible methods are less biased because they can be very wiggly. But this fact means that they must be more variable. They will change drastically with even slightly different training data. Less flexible methods estimate smoother functions. These smoother functions are simpler, so they are more biased, but they are considerably less variable. A dominant strategy that is extremely common in different machine learning methods is to purposefully decrease flexibility to increase bias but substantially reduce variance. This is purposeful thinking about the bias-variance trade-off in order to decrease test error overall and prevent overfitting. We'll come to see this trade-off in action across all of the methods that we explore. So in summary, we've introduced a distinction between parametric methods and nonparametric methods. Parametric methods simplify the task of estimating the function that relates the response to the predictors by assuming that the function looks a certain way. Nonparametric methods try to make fewer of those assumptions. We talked about a particular nonparametric method called K-nearest neighbors regression that only assumed that cases with similar predictors should have similar responses. We considered the differences in the estimated functions for different values of k and saw that this was a prime example of the bias-variance trade-off phenomenon in machine learning. Varying a tuning parameter to decrease bias essentially always increases variance, and vice versa. Clever machine learning methods capitalize on this idea to decrease test error overall by balancing model flexibility.